Okay, so what we do here is I'll write down the formula first and then we'll write the formula for the finite difference. So here's the formula for the heat conduction equation. We write it as the finite difference equation now. So alpha, so here's the expansion for the space discretization. I write it as Ti plus 1 comma j plus 1 minus 2I plus 1 j plus Ti plus 1 j minus 1, the whole thing divided by delta x square equals Ti plus 1j minus Ti j divided by delta t. Okay, so the left side is forward difference. So you can see it's forward difference over j because delta x is the variable component. And the right side is finite difference over delta t. So I is for delta t. So you see that j remains constant on the right side because that's the spatial component. On the left side, you see that I remains constant. There's I plus 1 appearing in all the three terms. And so that's because that's the time component. So what is difference between this formula and the earlier one? So here we have an implicit method. So notice that we have I plus 1, I plus 1, I plus 1 here. And if you go back to FTCS, here you'll see that we actually have I, and I. This is the only change. We just changed the index for this part. It's here it's Ti, and here it is Ti plus 1. That's it. Okay, and this is certainly going to make it actually much harder to solve. Not harder, not terribly hard, but harder. And then there's going to be no stability issues. So let's try to sort of simplify this. Okay, now remember everything, you typically know things at timestamp I, but you don't know anything about timestamp I plus 1. So what I need to do here is try to write or collect all the terms involving I plus 1 on one side and I on the other side. Those will be known. So I can write this as minus f t I plus 1 j plus 1 plus 1 plus 2f I plus 1 j and then finally minus f t I plus 1 j minus 1 equals Ti comma j. Okay, what is f? F is the same as before. It's alpha delta t divided by delta x square, where there's no condition on f. Okay, another thing to remember is that we typically know what this value is, but these things are unknown. So here's where the problem comes. There are four unknowns here, three unknowns here, Ti plus 1, j plus 1, Ti plus 1, j, Ti plus 1, j minus 1. But there's only one equation. So we cannot solve for those three constants with one equation. So what needs to be done is that we need to write this equation for every single grid point and then collect all the unknowns together and then solve for the unknowns. So in this case, because t is all linear, you'll end up with algebraic equations, something like ax equals b, and then you'll have to solve for the unknown x. And we'll do that for a problem. So this is the equation we were after. And this is implicit because we cannot solve for ti plus 1, j plus 1, pi plus 1, j, and ti plus 1, j minus 1 explicitly. Like there's no formula for it by itself, and we need to do something more than that. And then the thing is about this method is unconditionally stable. Okay, so typically stability is associated with solutions approaching infinity. That problem is not there here. It could be a problem for the other method. So the best way to illustrate this is to solve a problem. So let's do the same problem we did last time using this method. Okay, same problem. Given the heat conduction equation, given initial conditions IC, given boundary conditions BC, compute the solution temperature profile with those dx and dt. Okay, so first things first, let's just get what alpha f is. F is alpha delta t divided by delta x squared. It's going to be the same for this as the previous one, but let's just compute that here. Delta t is 0.1, delta x is 0.25. We squared that, and if you do the math on that, comes out to be 0.32. Okay, we'll use Tij as our time index, where the temperature profile, where I would be the time, index, so time index, and j would be the space or position index. Okay, also some other things. Here we have a grid for time, so Ti, that is I times delta T. So we would put I equals 0, 1. So we want to go up to 0.5 seconds. So I needs to go from 0, 1, 2, 3, 4, 5, and that will give us a time of 0, 0, 0.1, 0.2, 0.3, 0.4, 0.5. We'll stop there. And then for xj, we'll have j times delta x. So j would go, well, we need to go from 0 to 1, and delta x is 0.25. So 0, 1, 2, 3, I believe 4, and xj would be 0, 0.25, 0.5, 0.75, and 1.0. So when you have this t and x, what you're looking for is you probably want to show your solution as a table of all combinations of ti and xj. So it's basically tij. Okay, so there are a number of ways to do this. Last time I showed you, this basically boils down to bookkeeping. Last time I showed you, well, one way of doing this. I essentially set out by setting up this grid of I and j and then putting it there. This time we'll just follow a different method, and you can take whatever you like. Usually when you're constrained by space, like you are in exam, your best bet is to just write it in the form which you would present it, which will be a table. Yeah, question?
Sorry, can you go back to the original?
This one?
Can you scroll down, please?
Yeah.
All right, that's it. I just want to make sure I had the last line written down.
Sure.
Thanks.
Sure. So my suggestion is, well, that was another way. Here's another way where we'll just write the table we want. We We want the solution to be in a special way, the table for I and j. Let's create the table. Let's fill this up as much as we can without doing any problem solve that, without using the equations, and then we'll know what needs to be solved for. So let's just do that. So here is how we'll do it, slightly different from last time. This is my solution, right? But I start off with the solution table first, x and t. So x, I know it's 0, 0 0.25, 0 0.5, 0 0.75, and 1. And time I need to go 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. Okay, so filling this up is what I'm after, right? Each of these, if you think of this as a matrix, you have 1, 2, 3, 4, 6. So 6 here, and 1, 2, 3, 4, 5. So 6, 5, 30. So there are 30 sort of points in this matrix, 6 by 5 matrix. You need to fill each of these. Okay, so each time you put a value there, you get a point. So let's try to see how many we can get without actually solving the equation. Those will come from the boundary conditions and the initial conditions. So the initial condition given to us is that tx0 is 100x minus 100 times x minus x times 1 minus x. So let's just use that. So IC is t of 0 comma x is 100x 1 minus x. Okay, so what is t 0x? It's basically t I j. In fact, I is 0. I remember that this was, let me put it down in a different color here. If you look, write I values, this would be 0, 1, 2, 3, 4, and 5. And then if you write the j values, which I'll do on top, it'll be 0, 1, 2, 3, 4. Okay, so the 0 is for time, it's 0, so I is 0. Okay, so this basically gives us some things to work on. So t0 comma 0 is going to be what's that? This is j is 0. So j equals 0 means x is 0. So it'll be 100 times 0 times 1 minus 0 is 0. So that was super easy, 0. Then we have t 0 comma 1. What's the second index? 1. That's for j equals 1, but that's 0.25. So 100 times 0.25, 1 minus 0.25. That's going to be, I think it's 18.75. 0 comma 2, 100. The next value is 0.5. 1 minus 0.5 comes out to be 25. This is actually a symmetric profile. So it will be the same value as for 0.2575, 18.75, 0 comma 4, 100 times 1 times 1 minus 1, which is 0. So we are ready to fill this up. So we have 0, 18.75, 25, 18.75, and 0. So this entire row came from this IC, these values. Okay, so it was super easy to get that. Now, given that, there's more work we can do without actually solving the equations, which is we're given another condition, which is the boundary condition. Let's see what we can use that in order to fill this table. Okay, let's look at the other condition we given to us. It is t 0 comma t equals t1 comma t equals 0. So let me write that down. Boundary condition t 0 comma t is t1 comma t equals 0. So this index, the first index, well, here the yeah, so first index is x. So this is saying that what's the index for x which corresponds to 0? If you go back here and if you see x, so we know that tx or t0 t0 comma t would mean x is 0, which means that j is 0. So we need to choose, we have j comma, well, I comma 0, right, because this is the jth index, equals t, and that's the x index for that one is 4, right? For 1, if x equals 1, then index is 4. So t I comma 4 equals 0. Is that right? Right, that's right. Okay, so once we have that formula, now we can do this, is that that's true for any I. So we have t1 comma 0 equals t1 comma 4 equals 0, t2 comma 0 equals t2 comma 4 equals 0, t3 comma 0 equals t3 comma you know what, let me just make, instead of writing it this way, easiest way is to write, this is true for I equals 0, 1, 2, and I goes to all the way to 5. Okay, what this is saying is that everything in where j is equal to 0 or j equals 4 is basically going to be 0. So j equals 0 or j equals 4. If you go here, here j is 0 and j is 4. So everything in this row, sorry, this column is going to be 0. 0, 0, 0, 0, 0, 0. This was our, this is the boundary condition. Also this one actually. Okay, so we have identified how many? 6 on the left side, 6 on the right side, that's 12, and then 3 in the middle. 15 values already done. So since we have to identify 30 values, we're done with 15 without actually having solved, like, touched the partial differential equation. Okay, the remaining will come from actually solving the partial differential equation. Okay, so next, let's go and start using the equation. The equation is right here. Okay, let's take that equation, and since we're using this method, let's write the formula down. Okay, here f is 0.32. Okay, so here it is, the PDE. The formula is minus f ti plus 1j plus 1 plus 2f ti plus 1j minus f ti plus 1 j minus 1 equals ti comma j. Now we know that f is 0.32. In this particular case, let's just try to simplify as much as possible, because this will be an implicit method, and you'll see that it becomes pretty complex pretty quickly, that we don't want to deal with f's in our equation. So let's just try to write this down as a numeric equation. So 1 plus 2 times 0.32 is 1.64. So the methodology we'll use here is we'll try to write this equation for each. So we already know so this equation is, well, this we know the value here. We're going to write it down for I equals 1, and then I equals 2, and so on. So let's write I equals 1. Maybe I should write I equals 0 because I'm looking at this. I should write I equals 0, so that way I plus 1 is what I was trying to make equal to 1, which only happens when I equals 0. So I equals 0. So write it down as 0.32 t 0 comma j plus, sorry, 1 comma j plus 1.64 t 1 comma, was a thing I made an error here. This should be I plus 1 j plus 1. I plus 1 j plus 1, 1 j plus 1, 1 j minus 0.32, 1 j minus 1 equals t1 j. So this is true for all j's. Okay, so now we've broke, so this should be 0. Okay, so once we have it in this formula, in this way, now since we've put j equals I equals 1, we're essentially trying to get these values. And the way to get these values is now to vary the other value, which is the jth value. So we have, let's put j equals 0, 32 t 1 comma 1 plus 1.64 t 1 comma 0. There's a problem here. I can't put j equals 0 because if I put j equals 0, I'll get t1 comma 1, 0 minus 1, which is minus 1. I can't do that, right? So be careful. So I can't do for j equals 0. I should need to put j equals 1. So it'll be t1 comma 2, 1 comma 1, 0.32 t1 comma 0 equals t0 comma 1. Okay, so this is where I think the table will really help you. I need, some of these values are known. In fact, I can tell you very confidently with the implicit method, you will not know these values. But maybe you'll know some values. The boundary conditions you'll know. I think this one is known. So anything with index 0 is known because you saw here, if you see here, you know this is a boundary condition. Or if you think that's hard, go back over to the table. Anything with index 0, j equals 0, is going to be 0 in this. So this is going to be 0. And then 0 comma 1 is usually known. Everything at time index, the previous time index is known. So 0 comma 1, if you go back here, 0 comma 1 is 18.75. So we know that. So now we get this equation here with two unknowns. This unknown and this one is unknown. That's 0. So we cannot solve for two unknowns using one equation. So we need to just keep moving forward. Let's put j equals 2 in this equation, minus 0.32 t1. So j is 2. So 2 plus 1 is 3 plus 1.64 I comma j, 1 comma j, so 1 comma 2, minus 0.32 t1 comma j minus 1. So 2 minus 1 is 1 equals t0 comma 2. Okay, 0 comma 2 is something which should be in the table. So 0 comma 2. 0 is here, 2 is here, so it should be 25. Okay. 1, 3, 1, 2, 1, 1, all three of them are unfortunately not known. So if you go here, 1, 1 is this one, 1, 2 is this value, not known, and 1, 3 is this value. So these three values here are not known, so we cannot write them down. So we'll have to keep the equation as is. And then finally, we'll write j equals 3.32 t1. So j plus 1 is 3 plus 1 is 4 plus 1.64 t1 comma j is 3, so t1 comma 3 minus 0.32 t1 j minus 1 j minus 1, so 3 minus 1 is 2 equals t 0 comma j, so j is 3, so 0 comma 3. Okay, let's try to see what 0 comma 3 is from the table. Let's go to the table. 0 is here, 3 is here, so it is 18.75. Okay, out of all these values, I think t1 comma 4 is known, it's a boundary condition. So so I is 1, j is 4, I is 1, j equals 4, so it's this value, it's 0. And then 1 comma 3 and 1 comma 2 are going to be these values, 1 comma 2, 1 comma 3, they are unknown, so we can't write them down. So what we have effectively done is written three equations down, and those are actually three equations in three unknowns. So let's rewrite those three equations for j equals 1, j equals 2, j equals 3 as three linear algebraic equations, and then solve using, you can use, methods, we've talked about methods to solve them. In this case, we'll just use a/b to solve it. So here are the three equations. We'll call this 1. Okay, so from 1, we get these three equations. Point 32 t1 comma 2 plus 1.64 t1 comma 1 equals 18.75 minus 0.32 t1 comma 3 plus 1.64 t 1 comma 2 minus 0.32 t 1 comma 1 equals 25, and then 1.64 t 1 comma 3 minus 0.32 t 1 comma 2 equals 18.75. So three equations, three unknowns. So let's just write it down like this: t1 comma 1, 1 comma 2, 1 comma 3 equals 18.75, 25, 18.75. And then let's write this down. The first row of this equation would be is 1.64 in front of t11, and there's minus 0.32 in front of t12, so that would be the second first row, second column, and then 0 because there's no t13. Similarly, we can write minus 0.32, 1.64 minus 0.32 for the second equation, and for the third equation we have 0 minus 0.32, 1.64. So this is of the form ax equals b, x equals a inverse, or if you like in Octave or MATLAB, you can do a backslash b. We get, solving this, we get t1 comma 1 equals t1 comma 3. They have the same value. It's going to be a symmetric profile, is 15.595 t1 comma 2 is 21.33. Okay, so we can now go and populate this in our table. So our table will have these values are known: 15.595, 15.595, 18.0946. Okay, so this is just so much work to get just these three elements. We need to write three equations, which were here, and then we simplified them and then got the values for the constants. We unfortunately need to do the same thing for I equals 1. So we'll put I equals 1, then we'll put j equals 1, 2, 3, get three more equations. So I would like you to check this up. I'll give you the answer. So use the same procedure as I used. Put I equals 1, j equals 0, sorry, j should be 1, 2, and 3. Okay, so when you do that, you will get a 3 cross 3 matrix equation, which looks like this. Okay, it turns out that you'll get the same A matrix. This is the best part about these equations. You'll always get the same matrix. And that is one of the things which is exploited in any numerical package which does PDE, like ANSYS, which will solve the PDE in the backend, will actually use this particular nice result. The other thing which ANSYS uses to make these computations easy or fast. So we're looking at a small system because we want to do this by hand. But when you try to do this, so when you try to do this using a package like ANSYS, when you have a fine grid size, you'll see that this will be like 100 cross 100 matrix for A. And that is very, it is fast for a computer, but then if you're looking at a, not 100 actually is an underestimate, we will probably be in thousands anyway. It's a 1,000 by 1,000 matrix, probably still very straightforward for a computer. As it goes bigger and bigger, it's much, much harder to solve. It turns out that many times these particular matrices actually have lots of zeros appearing in them, and they usually will appear in the off-diagonal elements. So that is sort of something which they call sparsity in numerical programming. The sparsity means that you don't need to save them. They'll only save the non-zero elements in that matrix. So here, for example, there are 0 elements in row 1, column 3, row 3, column 1. So you never save them. You only save the ones which have non-zero values. And then there are special methods, which we've not talked about, which exploit the sparsity of the matrix, the zeros, to solve them much faster, okay? Which is beyond this course. But this is what you will get if you solve this set of equations. You get 13.0397, and t2 comma 2 equals 46. And then you need to repeat this I equals 2, 3, 4. But now you should have seen a pattern emerging from this, right? The left A matrix is the same. The B matrix is basically whatever you get here, and then it's just easy. So I'm going to fill up that table, okay, which is basically what you're going to fill up in the exam too.